This is Dr. Rob Cyrus. I am the carb addiction doc, and I am thrilled. In fact, both this person and myself just teared up a few seconds ago because I am thrilled to have a colleague and a mentor and someone I look up to. And there's not a lot of people I look up to with me today, Dr. Georgia Ede. And you know what I was telling Georgia a few minutes ago is that I've got a PhD on my shirt. We all have a bunch of degrees and qualifications, and she works at Harvard, which by itself is accolade, and the degrees and qualifications are nice and important. But I focus on how I feel when I interact with someone, both written and verbally and in conversation. And Georgia is one of the most inspiring, compassionate, empathetic, and succinct people I have heard speak, and who connected me. My presence at the Swiss Re conference was directly and exclusively because of her. And such an incredible mind in terms of seeing a problem and objectifying it. And that's what we're going to talk about today with her book that she's just published. She's able to see a problem and objectify it while having a wry sense of humor and humility about it. She really is, from a humanistic perspective, what I call a door opener, somebody that connects with people and you lean in and you want to spend time with her. Someone that I felt instantly comfortable with, looking up to and admiring for the talented manner in which she connects with people. And ultimately, that is so important because she is a psychiatrist. And I normally think of psychiatrists as people in the mental health space that write prescriptions. I see therapists that treat people. I see psychologists that test people, and psychiatrists write prescriptions. And you are not that. You are deep thinking, compassionate, and your book is part of that. And hearing you on stage speak, that's what you do. And you've written this wonderful book called Change Your Diet, Change Your Mind. And we're going to dig deep into that and nerd out a little bit about that. So welcome.
I don't know what to say. That was just the nicest introduction anybody's ever given me. Thank you so much.
And not a degree mentioned.
Right.
So let's dive into the deep end of this. Now I'm going to prod and poke some important questions here. Your first chapter speaks about mental health from a metabolic perspective, and I see mental health from a metabolic perspective, but there's also an organic component. To what extent is mental health, the global aspect of mental health and mental illness, organic, genetic versus metabolic? Are they separate? Are they linked? How do those concepts interact? I mean, how is it possible that schizophrenia can have a metabolic component to it?
Yeah, and so I mean, we could spend an hour talking about what the definitions of all three of those words are, you know. And so I mean, it's all connected, right? So so I mean, metabolism represents, I mean, depending on who you ask, just about everything every cell is doing all day long. So it's not just how it produces energy, how the cell produces energy, but how it takes care of itself, how it cleans up after itself, all of how it interacts with other cells. And so a metabolism, it's just the daily business of living and being a cell. And so of course, if metabolism isn't running properly, cell isn't working properly, the organ won't work properly. And depending on how you define metabolism, it could be, you can think of it as just about everything, or you can think about it more sort of in a more focused way about, how the cell breaks down fuel molecules and turns them into energy. And then what else it decides to do with those molecules.
Let me ask
Yeah.
you. Yeah, sorry to interrupt. I
Please,
dive a little bit. But
anytime.
the way I look at the brain, and as a surgeon with a little intrepidation and fear and lack of knowledge, but every cell has to live, has to repair itself, but it also has a particular function. It has a job. It goes out to work. Brain has a unique job in terms of mentation and regulation of a variety of functions. I mean, the brain cells and the neural network are unique in terms of the job that they do. And the question, and I understand that every cell has to repair itself, every cell has to, well, not the brain cells so much divide, but they have the metabolic part, they need energy to function. But how does that metabolism specifically, beneficially and negatively affect the job that the brain cells have to do?
Yeah, so the brain is a very high energy organ. So it uses about 10 times more energy than you would expect for an organ of its size because it's electrical. And generating electricity requires an awful lot of energy. So if you don't have a steady supply of high quality, reliable energy, and really just at every second of every day, the brain is not going to be able to work at its full capacity and something will go wrong. So it could be that, it's not able, that certain cells aren't able to fire when they're supposed to, or it could be that certain cells are firing when they're not supposed to. Or that certain, or they're not able to repair and maintain themselves, so they break down and they don't work at all. So there are lots of different things that could go wrong, and I think this is exactly why, to come back to your previous question about how can a disorder like schizophrenia be rooted in metabolic issues, but also depression and also dementia and also bipolar disorder, ADHD. How can all of these seemingly very different diagnoses potentially be rooted, at least in part, in the same problem? And I think that's really the mystery that I find so intriguing. And the way I think about it, and it's very simplistic, is, well, that might be where the genetics come in. That might be where your life experience up to that point comes in, or even your epigenetics, how your parents and grandparents lived their lives, and what kinds of insults you've already suffered in your life. So, they're always saying, well, people are always saying, oh, this runs in your family, dementia runs in your family, or depression runs in your family. You just have the genes for it, right? But these genes, our lifestyle and the way we eat, especially in how we live, decides which genes are going to be active and how active they're going to be. And so I do think we have some control over their expression, but I don't think, for the most part, I don't think that our DNA is our destiny. I think that, you could have 100 people in a room with insulin resistance. Not all of those people are going to get type 2 diabetes. Some of them are going to get dementia. Some of them are going to get obesity. Some of them are going to get fatty liver. So some of them are going to get cancer.
My viewpoint of the brain is it's just this mystical organ that can do so many crazy functions. And I use the word crazy colloquially. You're talking about a cell firing, and that's very sterile and an organic way of looking at the brain. What about our thoughts? What about our abstract views? What about the ability of me to work with my hands or talk? This is a highly coordinated intracellular link that is occurring in the brain. And what I'm looking at more from a brain function, you're looking at this organically, it's an electrical system, but the mystique of the brain and where I see the disruption going is not just single cells, but it's the coordination of various cells and pathways, white matter, gray matter. I mean, it's so intricate and so complex. And I understand we can get this down to a metabolic level. But as a psychiatrist, taking off your organic hat, how does all of that interplay? How does a lot of these diseases are expressive disorders.
Right.
And how do you take individual substrates and molecules and firing and create this wonderful thing, whether it's me appreciating those flowers behind you or being able to do a mathematical sum or even just talk and use my hands?
I mean, I think honestly, if I knew the answer to that question, I would win a Nobel Prize. It is I mean, the brain is beautifully mysterious, and it's been frustrating, for millennia, like trying to understand, where do thoughts come from? Where's the soul housed? What makes you, you, and me, when we're so genetically similar? It's just, how can we have this great diversity of human beings and thoughts and experiences and feelings? I mean, I think that's one of the beauties of one of the mysteries of life. I mean, the brain, because we can't see it or feel it or touch it or see it working, it's always been difficult for us to really understand it. And I think there's still so much that we have to learn. But one of the things I think that's really exciting right now about the field of psychiatry, I mean, psychiatry's been, after decades of standing still, is really taking a quantum leap forward. And I don't think that's an exaggeration. I think finally we have, I mean, we've been working in the dark for so long, kind of guessing at, well, I wonder why this person is depressed. I wonder which medication might help this person. It's all been guesswork, questionnaires and checking boxes and throwing spaghetti against the wall and seeing what sticks. And now we actually, when you start to appreciate that the brain is an organ like any other organ, unlike, but also is also an organ, it can malfunction if your metabolic health isn't good. And of course, and so if we step back, we zoom out. I mean, we've been trying to zoom in for so long and understand, but I think actually if you zoom out and think, oh, the brain's part of the body, it's an organ like any other organ. It can malfunction like any other organ can malfunction. Maybe it's not a spiritual deficit. Maybe it's not a deep characterological flaw. Maybe, as one of my patients said to me today, maybe there isn't anything wrong with me. Maybe there's something wrong with my diet. It's it's I mean, I just think it is extraordinarily complex and humbling, and at once just an organ like any other organ that needs the same care as every other organ does. And I think that has been useful to me. As much as I can remain in awe of the brain, I also can think of it as, okay, it needs energy, it needs fuel, it needs nutrients, it needs to be protected against, all the damage that our diet is doing to us, just like the rest of our cells do.
So to what extent, I love that narrative, to what extent is the DSM-5 and all these wonderful diagnoses, all those four-letter words that you were throwing out there, the ADHDs and that kind of thing, to what extent are those a magical, mystical cloak, as you said, of camouflaging something that we see observationally as a behavior? And what you've done is walk backwards, as you said, taking that bigger picture and said, look, forget about all that magical cloaking to explain something we can't explain. And let's look at the organic nature of the brain and see what it needs to optimally function. And if we give the brain the adequate substrates in the right balance, I hate that word, but in the right ratios, feed the brain what it optimally needs, it's going to function normally, and then we don't need to use these other words to explain metabolic maladaptation. Is that a reasonable assessment of where you're coming from in this book?
I think it's a beautiful summary of where I'm coming from in the book. And it really is that, I mean, what other creature on earth needs to understand how its brain works in order for it to function? I mean, I think it's fascinating. I love trying to understand the brain, but you shouldn't need to understand the brain in order for it to function well. It was designed, it evolved to function if you give it the right ingredients. And I think that it's mostly about that. Yes, there are other pieces to the puzzle, but why not start there with the most important piece, which is making sure the brain we nourish the brain with all essential nutrients. We protect the brain from damaging influences of these ultra processed non-food ingredients, which promote inflammation and oxidative stress and insulin resistance. And why not protect the brain's metabolism by protecting your metabolism, by keeping your glucose and insulin levels in a healthy range? If you do those three things, and they're really very basic in a lot, I mean, it took me 400 pages to explain, how it works, but it's really that simple. We really I mean, nutrition science has lost its way. Really since the 1950s, we've been completely off course. And that's why it took almost 400 pages to try to get people back on track.
Well, isn't that in
we're on the
large
wrong
part
path.
industry driven? Isn't that's not science driven, that's industry driven, whether it's the folks trying to protect tobacco by blaming fat, whether it's Coke trying to protect their product by saying we don't exercise enough, whether it's these pharma drugs, a myriad of psychiatric drugs. Most often we don't even know what they do, but we throw them at patients with DSM diagnoses and hope that they somehow magically work. So that's what we want to step away from. So you've really taken off your psychiatry hat and looked more at this from an organic chemistry hat. But you said something earlier on that the brain is like all other organs. But I'm going to disagree with you when we talk about nutrition, because the brain is encased in something that prevents it more than any other organ from getting adequate substrate. And that's called the blood-brain barrier. And it's a defense mechanism, but it's also a barrier to a large number of things that we consider to be essential to other organs from readily crossing into the brain. Long chain proteins, long chain amino acids, long chain fatty acids, they don't rapidly go across the blood-brain barrier. So by defending itself with this moat, I think of it as a castle, where the king is in the castle and you've got this moat around it. The problem is you can't get food into the brain as well as you can any other organ. And there's this dichotomy. So as you look at what essential substrates the brain needs to adequately function and to repair itself. And as you said, it's a very big spender of, it's a bit like my wife on Amazon. There's continuously Amazon trucks coming to the house because and I love her to bits, but so if I build a big fence around my house, what would the Amazon guys do with their delivery? They'd have little boxes and squeeze them through the fence. But how does the brain then get the substrates that you believe it needs? What are the essential substrates? How does the rest of the body break them down for delivery to the brain in adequate amounts? We know long chain fatty acids just don't cross. And how do these substrates cross the brain? That's the part A of the question. The second question is, a lot of the regulatory functions of substrate, the big hormones, are proteins, insulin, glucagon, and they don't easily cross into the brain. But we know that the brain has its own form of glucagon. It's got its own form of insulin. It's got its own hormones that we might not even have described yet. And it makes them inside of the brain. So the question is, how does the food that we eat get into the brain? What foods are essential in what format? And, the liver, for example, takes amino acids, makes them into protein, but they don't easily get into the brain. Same thing with fat. So how do you get them into the brain? How do you cross this barrier? And what do you believe are the essential substrates? And to what degree is there internal hormonal regulation within the brain that is exclusive?
So many questions. So let me sort of step back and say, okay, how does the brain get the substrates? How does it get the molecules that it needs? How does it get the vitamins, the minerals, the fatty acids, the amino acids, and the fuel molecules, largely glucose and ketones? How does it get those molecules?
Is the brain sugar dependent?
It does require some glucose at all times.
Okay, but we don't have to eat that glucose because the liver makes it.
Correct. You can get your glucose from outside your body from your diet or from inside your body from fat and protein. But either way, the brain does require some glucose at all times, but the majority of its fuel needs can be met by ketones, but not 100% of its fuel needs. And that's because there are certain functions in the brain that do require glucose or function at least optimally on glucose. So for example, there are certain cells, the glutamatergic cells, for example, they make glutamate, which is the brain's primary excitatory neurotransmitter. They need fast energy. And one of the advantages glucose has over ketones is that glucose burns faster. So if you have a rapid fire cell, you may need to function optimally, you may want to burn a substrate that burns more quickly. And so you can chop up glucose much more quickly than you can you can chop up ketones. The other thing is that there is a construction pathway in cells called the pentose phosphate pathway that's used to build certain molecules, include antioxidants and nucleic acids. Glucose is the only molecule that can go through that pathway because ketones are too small. So we do need some glucose at all times, but the majority of the fuel needs of the brain can be met by ketones if we choose to live that way.
The only other comment there is that glucose, and I like that explanation of the pentose pathway, because for the most part, I look at glucose as an essential fuel, but it is not really adaptable into structure. Whereas ketones fulfill two separate roles. They have a fuel, an energy role, but the brain itself can turn ketones into longer fatty acids and can use them because they cross the blood-brain barrier very easily, and it can rebuild chains. It's like individual pearls going across, and then the brain itself can build the the pearl string or the pearl chain to be used as structural fat for the cell wall, for the organelles that are turning over. Is that correct? Is that an appropriate summary that there's more flexibility, biologic flexibility with ketones that can be triaged toward fuel or structure as opposed to glucose?
I think it depends on what you're trying to make and what the hormonal situation is, but the brain does have that flexibility. And so, for example, you know, uh, the brain is full of cholesterol, lots and lots of cholesterol.
But that's bad. Doesn't that kill the brain?
Yes, the brain makes it on purpose because it's on a suicide mission.
Does the brain make cholesterol, or does it cross the blood-brain barrier?
So this is one of the when you said, you know, how does it get everything it needs, and this blood-brain barrier is an actual barrier in some cases. Cholesterol is the best example of that, because when it comes to amino acids, there are special transport molecules that can, you know, usher the amino acids across the blood-brain barrier. They don't diffuse, you know, simply across. They do need a carrier molecule. Glucose is also has a carrier molecule, as does insulin, but cholesterol is too big and bulky to cross the blood-brain barrier. And so even though the brain contains 20% of the body's cholesterol, again, 10 times more than you would expect for an organ of its size, rich in cholesterol, not a single molecule of that cholesterol comes from the food you eat. Not a single molecule of it comes from your bloodstream. The brain makes every molecule of cholesterol that it needs on site from
Do
scratch.
you know if it uses the HMG-CoA reductase pathway?
Of course it does, yes.
And that pathway is regulated by insulin in the liver. Is it also regulated by insulin in the brain? Do you know?
I would assume so, although I haven't looked specifically at that, but I would assume so.
So the other question then, I meander. I don't
Go,
flow.
go, that's fine.
So the next question is, when people are on statins or cholesterol lowering medications that interfere with HMG-CoA reductase in the liver, do they cross the blood-brain barrier, and do they have a similar cholesterol lowering effect in the brain?
They absolutely do. In fact, yeah,
Wait, stop.
yes,
Can you repeat that again? This is, I will do that from time to time when there's something
please,
that blows
anytime.
my brain. And say that again.
So all statin medications cross the blood-brain barrier, some much more easily than others, Lipitor and Zocor, and others with much more difficulty because they're not as fat soluble, but they all do to a certain extent. So when the statins cross the blood-brain barrier, they do the very same thing in the brain that they do in the rest of the body, which is they turn down the activity of HMG-CoA reductase, which is the enzyme that allows the brain to make the vital cholesterol molecules that it needs to function
Wait, they're
properly.
not vital, because surely God in nature made the brain make cholesterol as a kill switch. Because that's what all the statin people are telling us, aren't they? Is that this cholesterol is so bad for you, and somewhere along the line, God or nature, whichever pathway you follow, said, hey, you've lived long enough. We're going to put a kill switch in here and create Alzheimer's and a kill switch in your liver to kill you. Or maybe cholesterol is biologically necessary for those organs.
You know, I wondered that myself because you look at every membrane in the body, it seems to have cholesterol in it. So, you know, it seems to me to be rather dangerous that we're constructed this way.
I mean, it just boggles my mind that, and I bet you that nobody or extremely few people that prescribe statin routinely for cardiovascular risk even consider or know what you just said. And yet that is so profound that pathway is necessary. And we know that the brain is about 5% of the body weight and contains about 20% of the body's cholesterol. That's a number that I've heard. Do you think that's correct?
The number that I've seen so often is 2% versus 20%.
Okay, two versus 20. My brain's bigger than yours, then I'm 5%.
Touche.
No, but it's still 20% of that ratio is even bigger. The two
Yes,
to
exactly.
20.
Exactly.
Wow. Okay.
Yeah.
And statins block that. So what is that? What is the role of cholesterol then? And what happens when you reduce cholesterol production in the brain?
Well, you know, it's a very well documented side effect, and also clinically, I've observed it many times in patients. Brain fog and memory problems, cognitive impairment from statins is not uncommon. And I know this not only because there have been cases reported, but also because I've worked with, patients for so many years now who take, because oh my gosh, so many people take a statin medication now. And so I've worked with lots and lots of patients who have started statins. Their memory, seems to become impaired, or they become foggier, have trouble word finding, things like that. They stop the statin, their brain clears up. They go back on a different statin because eventually someone convinces them that they should. Lo and behold, the brain fog comes back. Now, this doesn't happen to everybody, but it's happened enough times for me to be convinced that this is not a fluke.
And it's interesting. To corroborate that, I think you know this person. He's a good friend and colleague of ours, Stephen Cunane, who works
Oh
in
yeah.
the space. And Stephen quotes often a study of, I think it was American soldiers, veterans, that were on statins, and they had a cognitive impairment study done, uh, a test, a quiz, on statins. They then took them off statins, I believe, for 8 weeks, and their cognitive impairment improved significantly. They then put them back on the statins, and they saw the same deterioration over time. So that again corroborated that concept, but I didn't realize that the pathways you've just elaborated on that, and that's raised my knowledge level. The question then along those lines is, over time, does that cognitive impairment, because Stevens demonstrated early cognitive impairment is reversible, but does that eventually become permanent? Is there enough of an injury to permanently lose or have that cognitive impairment?
I don't know. I mean, I think it would depend on the degree and the duration of the impairment, because if you think about what all that cholesterol is doing up there in the brain, so cholesterol is an essential component of every membrane of every cell in the whole body, so not just every brain cell. And the brain is rich in cholesterol, so rich in cholesterol, ultra rich in cholesterol, because it's richer in membranes than most other organs in the body. Not just when you think about myelin. So myelin is the insulating the insulating material that winds around all of our circuits, our brain circuits, and networks, so that electricity can be conducted efficiently and rapidly. So what myelin is it's just a huge, very thick coil of very tightly wound membranes. That's a lot of cholesterol concentrated in that insulating material. So just imagine if you didn't have enough cholesterol. I mean, cholesterol does a variety of things in the brain. Not only is it wound up in all that myelin, but also it's a vital component of something called a lipid raft, which is a stiffened area of brain cells where communication takes place, and where that allows cell migration to take place. So it kind of guides nerve endings to their destinations when brain cells are developing. So lots and lots of important functions. So just imagine if you didn't have enough of those
And what
molecules.
is the consumed substrate? You say the brain produces cholesterol. What does the brain make cholesterol out of?
Well, just about every cell in the body can make cholesterol, and it can really make it out of anything because it's just carbon, hydrogen, and oxygen. So you can make it out of glucose, you can make it out of fat. It really doesn't, you can use whatever substrate you have handy. And I haven't looked specifically to see what the brain's favorite substrate is to make
Well, you see, my
cholesterol.
understanding is that it's ketones, and that
Huh.
the brain is much more adept to use ketones toward cholesterol, and the glucose pathway is, again, I'm speaking under correction, so this needs to be researched and corroborated. But the reason I'm asking that is because as a pediatric doctor, I deal a lot with children, and one of the things that I've written a book chapter on is autism spectrum disorder. And
Uh-huh.
autism spectrum disorder, there are a variety of supposed causes, but our philosophy and the science behind what we do is that in these families that are highly glucose dominant, they have insulin resistance, but also the substrate that triages toward cholesterol production in the brain is at a deficiency, both lipid and cholesterol. And what we're talking about in utero and in the first 5 years of life is human beings are the only species that structurally still continue to grow their brain after birth. All other mammals are born with a structurally complete brain. And we're still in the developmental phase. And if you don't have adequate ketogenic structure, we have the brown fat as a bit of a source, but we don't have that adequate fat. We find that there is a maldevelopment of the white matter of the brain. So as you said, those oligodendrocytes, the communicating fibers of the white matter don't communicate well enough. And the way I look at it, it's like the old telephone operator where the wires aren't plugged in properly. And that structural deficit is a metabolic dysfunction of a lack of adequate structure, or the other way I can explain it in colloquial terms, the three little pigs. You can build your house of straw, you can build your house of sticks, but it doesn't do so well. That's when you're using glucose. But if you use fat and you use ketones, you build your house out of brick. And that's kind of the way that a few folks that I've spoken to in the neuroscience departments have explained the development of white matter. And axonal deficit on MRI at 3 months of age can already predict the presence of autism spectrum disorder on an MRI. But here's the problem. Autism spectrum disorder can be predicted at 3 months of age, but it is a clinical diagnosis that is typically only made at 8 years of age. There's no structural element to the diagnosis of autism, which to my mind is lunacy.
There's no structural element to the diagnosis of any psychiatric disorder.
So that is really fascinating. I mean, the whole cholesterol narrative is fascinating. What other, so we've talked about cholesterol. How, and obviously the lipid membranes are all fat with a little bit of protein. How important is protein and amino acids, both structurally as proteins, and then we hear about taurine, we hear about these individual amino acids. How important are amino acids as neurotransmitters, as other parts of the functionality of the brain, and which amino acids are important in the brain? We hear tryptophan, and which ones do you think are essential in our diet? How do they cross, and which ones are important in the brain?
Well, the brain needs all essential amino acids, just like every other organ does. But there are some amino acids, of course, that are used to build specific neurotransmitters, like tryptophan with serotonin and dopamine and so forth. But then there are also individual amino acids that function as neurotransmitters throughout the brain. And so for glycine, for example, I mean, there are many different examples of this. So some amino acids, individual amino acids, actually function as neurotransmitters without having to be built into a larger protein. So if you don't have enough of all of the amino acids that you need at any given time, something could go wrong. And I think this is why it's really important for there to be enough protein available for the brain. I mean, we often think about, it's just so funny to me how we think of carbohydrate and serotonin as related to each other, that if you don't eat enough carbohydrate, you're not going to somehow have enough serotonin in your
Those are
brain.
amino acids. And
Exactly.
if you look at amino acids, there are 20 or 21 amino acids, of which I believe it's 9 that are essential.
Yes.
You cannot produce them. You can interchange a lot of the simple amino acids, but certain of them, like glutamine, cannot cross the gut barrier very easily. Others are essential; they have to be consumed. Am I correct in thinking that the only place that you get all 21 amino acids in the correct ratio is from animal products?
That is absolutely correct. Yes.
And so that's an important concept to understand right there, that a protein bar or a protein shake is not going to give you all 21. And these amino acid powders, and certainly a lot of the plants may have a fraction of them in, but not the whole lot. The second question, though, is, are any of these, because if you can interchange amino acids that are necessary in the brain, who cares? But are some of the amino acids in the brain essential amino acids that have to be consumed?
Well,
Of the 9 that are essential,
oh,
I think it's phenylalanine. I keep having
yeah,
to
sure,
look at
sure,
the list. But
sure, sure.
are those important to the brain? Because if we're not getting adequate essential amino acids in our food, that means automatically there's a deficit in the brain.
Oh, of course. I mean, they're essential because they're essential. And so, yes, the brain does require all essential amino acids. And you're absolutely right that while you can, I mean, you can certainly obtain, if you plan carefully and have the right information, you can meet your essential amino acid requirements, even without eating any animal foods at all. But it does require special planning. It does require a special knowledge, and it almost always requires more food. and because the quality of it's not, as you say, you may be able to find in certain foods, say tofu, for example, you may be able to find all of the essential amino acids there, but they're not always going to be in as robust the ratios and amounts as you would hope for. So tofu is perhaps the most the best plant food source of amino acids. You can get all your amino acids needs met from tofu, but there are risks associated with eating lots of soy protein, soy as a food, of course. But when you eat an animal food, you never need to worry about that because all of the amino acids are there and in plentiful amounts and in the right amounts. So you don't need to overeat, lots and lots of calories to get your amino acids met.
Right.
It's not just we we don't eat foods for protein. We eat foods for those of individual amino acids. So there are plant foods that have plenty of protein in them, but that doesn't necessarily mean they have all of the amino acids you're looking for in the right amounts.
So along those lines, we know that there are around, I don't know the exact number, nobody knows the exact number, but around 15 to 20 different glucagon molecules. And the brain has, as far as I'm aware, unique glucagon structures. We're still trying to work all of that stuff out. It's not one molecule. There's several molecules. The question, and the brain, as far as I'm aware, has its own subset of glucagon molecules that are only found in the brain or are in high concentration in the brain. So glucagon does exist in the brain. I don't know if you know the answer to this, but while we're talking about protein, the liver is very good using glucagon for gluconeogenesis to convert protein into other substrates, especially energy. Does the brain have that capacity?
This is actually something I don't know anything about. So if there's something you know about it, I would love to learn it.
I spoke to a biochemist PhD student a little while ago, just a wonderful talk, and they do work with glioblastomas. And there was something that came up about the different glucagon molecules, and the glucagon molecule that we measure at LabCorp Request is not. It's a decayed molecule of glucagon. So I don't know much about it. I think it bears a little bit of witness, but it'll be interesting to see if the brain is capable of transforming amino acids on the other side of the blood-brain barrier. I don't know. I don't know. I'm just, we were talking about amino acids and I want to complete that.
No, I love that. I mean, I love thinking about things that I haven't thought about before. So I just don't know the answer. So I'm glad to acknowledge that.
And we know glucagon's there, and glucagon does have a gluconeogenic function. So it's just interesting to ask that question. The next part goes to some of the electrolytes. And as you said earlier on, a lot of these substrates have to move across on a carrier molecule or use an exchange. We know there's a glucose-sodium exchange. And this is not just psychiatry, it's more neurology. But as you said, there's very little difference between the two. One is imagination. The other one is real organic disease. A friend of ours, Angela Stanton, is a big person on migraines, and she talks about a mismatch between glucose and sodium transport, and that specific areas of the brain tend to swell up with, when there's a mismatch, they swell up with intracellular glucose transport without the sodium coming out. How important is, because salt is very bad for your blood pressure. You know that, don't you? How important is sodium chloride, salt, and other electrolytes in the brain?
Yeah, so I mean, that's the electrolytes, electricity, right? So the brain can't generate all of that beautiful electricity without mineral salts. And sodium, potassium, calcium, magnesium, um, many minerals are involved, but the ones we think about most commonly are sodium and potassium, because that's where when the nerve is when the neuron is getting primed to fire, it creates that imbalance between sodium and potassium across its membrane. And what you just said was so on point, because when in so many conditions, for example, bipolar disorder and epilepsy, you can see too much sodium inside the neuron. And one of the ways that both the ketogenic diet and anticonvulsant medications work is by reducing intracellular sodium, so that because when you get too much sodium inside, you've got a hyperexcitable cell. You get a cell that's that is hyperactive. So this is one of the ways in which a seemingly simple mineral imbalance can cause havoc, either psychologically and or physically, because you've got to have just that right balance. You have to have all those molecules, all those ions exactly where they need to be at exactly the right times, or else the brain doesn't function properly.
And isn't that the place where really, of anywhere in the biologic space, with epilepsy, there is relative consensus, especially medically resistant pediatric epilepsy? Isn't that the one place where we're consistently comfortable with a ketogenic diet?
Well, I think so. And I think, although I don't, I don't understand why it's still not used very often and why it's still so hard for people to find that kind of care. But yes, I do think that for some reason we make an exception for epilepsy, maybe because it's been studied for over 100 years now. So maybe that's how long it takes to get comfortable.
So how different is epilepsy from ADHD? You mean you kind of use those two, and they obviously have different expressions. But is there more similarity between them than a difference? Certainly from the substrate biochemistry side of things.
Yeah, I think with all brain conditions, with all psychiatric conditions, if the metabolism isn't, if you've got poor metabolic health, if the brain metabolism isn't functioning properly, if you either have an excess of glucose inside the brain, which you can have, or you have an insulin deficit, which and this is very common in people with insulin resistance, then lots of systems are going to malfunction. They're just going to malfunction in different ways in different people. So, I mean, I've seen time and time again in my own practice, and I know there's a study being planned on this finally. Time and time again in my own practice, people with ADHD being able to stop their stimulant medication and function well when they're in ketosis. And so clearly there's an energy component to at least the many people that I've seen with ADHD, able to function without.
But that's the question. Is it an energy issue, or is it a sodium glucose issue? Is it again, you
They're
mentioned,
connected. It's all,
right,
how do
and
you how do
that's
you how do you pull it apart, right?
oh, you're exactly right. But I mean, that's just when you were talking, that connected with me. Is it truly an energy issue, or is it perhaps shift of these molecules and these ions across membranes that's affecting the intracellular ability to fire and to do certain things?
But they're connected because most of the ATP, most of the energy, the currency that the brain is used to fuel the sodium potassium pump that creates that imbalance between the salts in the first place across the membrane. If you don't have enough energy to keep those pumps running, you're not going to be able to generate that very strong electrical differential across the neuronal membrane.
Okay. So the next question is, does the brain require, or does it use, or are any of the steroid hormones important in the brain? And so generally, are there steroid hormones that are in the brain? And here's really, from a lay perspective, where I'm going is, and I've got to be very cautious here in the current climate, but I hear a lot of my females, especially perimenopause, oh, I got brain fog, and there is this association, and I'm using that word association, between female hormonal changes, often at that time of their lives, and brain changes, brain fog, fatigue, and those are steroid hormones: progesterone, estrogen, testosterone, DHEA, pregnenolone. And there's this association with brain changes and brain capacity and these hormones. And a lot of the functional medicine doctors will say, oh, let's put you on these super high doses of these hormones. I had somebody as a patient just the other day who was on ridiculously high doses because it was there to treat their brain function. And testosterone does have a profound effect when it's elevated in a woman, of reducing that brain fog, giving them energy. And the question I have at an organic level like this, what do those steroid hormones, do they have a true role to play inside the brain? Is that more associative anecdote? Do you have any light to shed on, and for the males as well, but really I hear it all the time with females, what correlation, is there any biochemical connection between the sex hormones, the steroid hormones? We know that they are triggered by the gonadotropins in the brain. Do you know anything about that? Can you shed any light on how that impacts people's perception of fatigue and brain fog?
Yeah, so I mean, I can't answer in as much detail as I would like because it's one of those areas that I would is on my list of things to study because I've become recently very fascinated as a 59-year-old woman with lots and lots of middle-aged and perimenopausal and postmenopausal patients, really fascinated with this question. But I can tell you what I do know so far, and what some of the things I'd love to know more about. So estrogen receptors are scattered throughout the brain. They are not there for no reason. So clearly it's at least a role for estrogen.
There are estrogen receptors in the brain,
Oh, yes.
which means estrogen has to be able to get into the brain.
Yes.
It's not made in the brain, is it?
I don't think so.
Okay. I don't
But
think so either. I've not heard of that,
I've
but
never checked to be
right,
sure,
I've
but
not
I
heard of
don't
that.
believe
We
so.
know that the pituitary gland is very important as a hormonal function. We're going to talk about that in a little bit, but there are estrogen receptors in the brain.
Yes, there are.
Wow.
And
Okay.
so, oh yes, there
And what
definitely are.
about do you know if there are progesterone receptors in the brain?
I haven't,
Testosterone receptors?
I imagine there are, but I have not checked to be sure, so don't quote me on that.
One of the issues that we know about insulin is that we've locked into insulin as our cognitive dissonance focuses on insulin as the molecule that regulates blood sugar, and it actually doesn't. Glucagon is the molecule in healthy people that regulates blood sugar, but insulin has a variety of other functions. Protein synthesis, cholesterol synthesis regulation, steroid hormones. So a variety of other issues unrelated to glucose metabolism. And
Yes.
one of the issues with estrogen, progesterone, testosterone, the precursors, is yes, they control reproduction. But the question is, have we, from a cognitive dissonance perspective, locked into those hormones so much as controlling reproduction and sex that we haven't shed light on or focused on ancillary non-reproductive functions of those hormones? When I look at the four anabolic hormones, it's insulin, human growth hormone, T3, and testosterone. Testosterone is a growth hormone, and it's not in its sexual capacity, but in its metabolic anabolic capacity. And we think, Arnold Schwarzenegger testosterone, so we misuse it. But the question is, are these hormones like insulin quarterback hormones for other functions, perhaps in a cyclical fashion, that have nothing to do with sex or sex reproduction? And I don't know the answer. I'm just asking that question.
I
And
do know part of the answer.
yes. Oh, good, 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 good.
Again, as a 59-year-old woman, I'm speaking from experience. So, I will share something from my own personal experience that your viewers may find useful. This is not medical advice. This is not meant to be taken. This is just my experience. So I've eaten a ketogenic diet for the better part of since 2012, so 12 years for the most part. I've had my time away from it and my time returning to it, right? But for the most, I really say almost the entire time. And so as I progressed through my late 40s and early 50s, that diet became less and less helpful to me. And I had to become more and more restrictive with my diet because I had lots and lots of food sensitivities and other kinds of issues, fibromyalgia, chronic fatigue, IBS, migraines, and things that I had originally addressed fully by switching to a low plant ketogenic diet that just included the foods that agreed with me. So it was a food sensitivity modified ketogenic diet. It worked beautifully for me for years. And then it started to not work quite as well as I sort of rounded the corner into a perimenopause. And for several years it kind of went on like that. And I just thought, okay, well, this is the natural order of things. and I will, just take it as it comes, and eventually I'll come out the other side. But what was very interesting to me was, I mean, I didn't mind that, my body shape was changing, or that I was gaining weight in this different way or anything like that. Even the hot flashes, I didn't mind. What I minded was I couldn't exercise anymore, because I could literally, you could look at me the wrong way and I would develop a tendonitis in whatever joint you were
Wow.
looking at the wrong way. And I could step to the left and my ankle wouldn't work for 3 months. It was unbelievable. And I thought, how am I going to keep myself in shape? How am I going to keep myself healthy? So I thought, what's different? Why is this happening to me now? I thought, I wonder if menopause has anything to do with it. It never crossed my mind, right? I start reading the literature. Lo and behold, estrogen is required for maintaining tendon health,
Wow. Okay. So it's
collagen synthesis.
right. Collagen, and there are multiple things that go into that, but a lot of the steroid hormones, vitamin D is a steroid hormone. So that is interesting. And then how did you correct that?
Estrogen replacement. And this is my own, again, my own N of one. So I had these multiple tendon injuries building up. At one point, I had 3 or 4 of these going on at the same time. I was seeing physical therapists. I was taking non-steroidal inflammatories. I was doing all kinds of special things for myself, and using creams and all kinds of massage guns and everything. Nothing worked.
Hmm.
3 days after starting an estradiol patch, it all disappeared and it never came back.
Wow.
So I'm a believer. And now the other thing that fascinated me was that I learned that estrogen helps to maintain the gut barrier, and which also makes sense if you think about it. And some of my food sensitivities improved as well, which I never thought would improve in the
Interesting.
rest of my life. So this is a very fascinating area that I have not had time to research because I've been writing this book about the brain.
Right.
But,
But
uh, but
it's
I
good
love
the
that you
receptors
asked
on
this,
the
because
brain.
we have to think about, there's so much we don't know and we forget to think about. And
Right.
questions we're not asking are so important.
Well, that brings me to the next question I was about to ask, because it's a little bit of a pivot. We're talking about the substrates. We haven't completed the list. But what you're saying is that estrogen appears to have an anti-inflammatory or a collagen repair role to it.
Yes.
And a large part of the challenges with a high carbohydrate diet is that glucose in excess in any space in the body triggers an inflammatory response. How does the brain deal with, and what is inflammation in the brain that may be different from other organs?
Yeah. So, so many questions within that question. I think that you're absolutely right that wherever there's too much sugar, you will see inflammation. And the brain does not put up a barrier against glucose entering, because it's so dependent on glucose. It's really quite easy for glucose to cross into the brain, and the level of glucose inside the brain is proportional to the level in the bloodstream. It's not the same. It's in fact much, much lower. In the brain, the level is about 80% lower in a healthy individual, than the glucose level inside the brain is about 80% lower than the glucose level in the bloodstream. And
Let me stop you for 1 second.
yes,
Is insulin required to get sugar to enter brain cells?
it depends on, so not usually. So most glucose entry into most brain cells is insulin independent.
So it's is it a GLUT4 receptor, or which?
I always mix
But
the
it's the
numbers.
insulin
I believe it's
independent.
yeah, I'm pretty sure it's
Yeah,
GLUT4.
yeah.
But I always mix the numbers
I
up.
also mix them up.
So, I, so there are certain cell types. A good example would be the cells of the hippocampus, the brain's learning and memory center. Um, there's a certain amount of glucose that comes in, without any insulin, just at baseline, the baseline amount flowing into the cell. But then the hippocampus needs so much energy to do its important work of making memories, that it requires extra boosts of glucose beyond that baseline flow. And those extra boosts of glucose do require insulin. So they have a different glucose receptor, which is insulin sensitive. So if you have an insulin deficit inside the brain, which everybody with insulin resistance does, which is now the majority of us, then your hippocampus is not going to get access to enough glucose.
Well, is it an
You
insulin?
struggle to record new
Right.
memories.
Does insulin cross the blood-brain barrier fairly easily?
With a receptor, there's an insulin receptor on the blood-brain barrier.
There is. Okay. Okay. So
And
yeah, that so
every cell inside the brain has insulin receptors, but most cells do not require insulin in order to allow glucose in, at least a certain amount of glucose.
so that hippocampus that is then it most likely, and you can correct me if I'm wrong, can arguably use ketones and glucose as a combined fuel source. But when you're hyperinsulinemic, you shut off ketogenesis. So
Exactly.
now you've got a single fuel source, and then if you've got the insulin blockade, either deficit of insulin or receptor blockade, you're not getting. So these cells are running at an energy deficit.
Yes, exactly. And that's why short-term memory is the first thing to go in dementia, because it's making new memories that requires those extra boosts of energy.
Interesting. And how does inflammation complicate that?
Yeah, so inflammation is it's physically damaging to the brain. There are many different kinds of inflammation, there are many different definitions of inflammation and types. So I give one example in the book so that people can kind of visualize what's happening. So if you've got too much glucose in the brain, which you will if you're eating too many of the wrong carbohydrates too often, then the glucose level inside the brain will be too, every time you get a glucose spike in the bloodstream, you will also get a glucose spike in the brain because they're proportional to each other. So the brain is very, very sensitive to glucose, and that's why it keeps the level so much lower than in the bloodstream. So when there's excess glucose in the brain, that excess glucose literally sticks to proteins and lipids and nucleic acids, all the and it really cripples them, kind of caramelizes them into these dysfunctional clusters that can accumulate and interfere with normal cell function. So but the brain doesn't take that lying down. It has an immune system, and the immune cells of the brain, as they're patrolling the area, they say, oh, what are these sticky clusters? We need to get rid of these. So they deliberately release inflammatory cytokines, these sort of SOS signals, and oxygen-free radicals.
So that process is intact and functional in the brain.
Yes, yes. So that's inside the brain's immune system. It's the normal, healthy first phase of the immune response to any threat, whether it's
Is arachidonic acid and 6-omega fatty acids involved in that pathway?
Oh, yes, of course. Yeah.
Which are the seed
That's all
oils,
part of the
which are the seed
inflammatory
oils,
path.
by the way, for those that don't know them by that.
Exactly. So yeah, so you have this natural inflammatory response. It's kind of, you sound the alarm, we've got a problem, and all these molecules are released, these signaling molecules, to kind of call for help, and then sort of clean up the area. And then there's supposed to be a healing phase that takes place after
Is there
that.
an immune cellular response in the brain? The white cells, the leukocytes, the neutrophils, the macrophages, are they able to cross, or is this primarily a chemical response?
So there's also a cellular response, but these are the cells inside the brain. There are immune cells inside the brain. So
Okay.
they are what are doing the patrolling. Is a particular type of glial cell. So yes, and they can morph just like a macrophage. They can morph and they can engulf and they can do all those
And
wonderful.
those are the cells that form glioblastomas or glioblastomas,
I believe, yes, exactly. Glioblastoma,
which
yes.
we're seeing in epidemic proportions now. And I wonder
My
if that,
gosh, I know. It used
well,
to be such a rare diagnosis, and now, I mean, I hear about somebody developing glioblastoma somehow through my networks. I mean, once a week it feels like.
and the ketogenic diet we're starting to find out, Siegfried and those folks has a significant role to play in having that. So I just wonder if these are the immune cells that are responding to this inflammation and they're ramping up, which means they have to divide and breed very rapidly. When those soldiers are having to fight big wars continuously, does that not open up the door to dysregulation in terms of their death rate? And I wonder if the
Without question. So because what happens is inflammation, and so the inflammation from the cytokines and the reactive oxygen species, these oxygen-free radicals, which are released as part of the immune response, these create an imbalance in neurotransmitters. For example, they tilt your glutamate GABA system far, like really extremely towards glutamate and away from GABA. So GABA is the brain's calming neurotransmitter, primary calming, and then glutamate is the brain's primary excitatory neurotransmitter. So now you've got less GABA and up to 100 times more glutamate than baseline. And glutamate, with too much glutamate in the brain, you can end up with a situation called glutamate excitotoxicity. And if you get too much glutamate in the brain, is physically damaging to the brain. And so it's normal to turn glutamate on like this in an emergency, but it's not normal to leave it on and to stimulate it 3, 4, 5, 6 times a day by eating these refined carbohydrates, which are spiking your brain sugar repeatedly throughout the day and well into the night.
Wow.
There are many different sort of pleasure and reward molecules in the brain that reinforce behaviors. And as you mentioned some of them. So for example, the opiate receptors, the opiate systems in the brain, right? And the endocannabinoids and dopamine.
Which is like marijuana, by the way. The endocannabinoids are marijuana type receptors.
Exactly. Yeah. And even serotonin and oxytocin, like there are lots of different molecules in the brain that help us to feel better in various degrees. And they can be hyperstimulated by unnatural stimuli, or they can be functionally stimulated in terms of our natural drive for pleasurable things. I mean, if food weren't somewhat pleasurable, we'd all starve to death. So
Right.
I think it's so one of the things I learned from you was about this effort-based reward system that builds self-esteem and self-confidence. Was a really, really useful concept to me when I first heard you talk about it a number of years ago. And I think it's a really, really beautiful way of thinking about it and approaching a lot of these issues. So when you combine healthy nutritional principles with healthy metabolic principles and healthy behavioral principles, when you put all those things together, and then for some people, I mean, I think for everybody, to some extent, there's also this sort of less easily defined sort of spiritual element too that has to come into play, and a social and spiritual element too. So when you've got all of these lined up just right, people are able to recover and feel well and enjoy their lives without turning to not just cope with, but enjoy their lives without those hyper stimulating behaviors and vices. I mean, it's pretty difficult. I mean, I do think that the hardest thing about my work isn't explaining the chemistry of it, or helping people transition to a ketogenic diet, or whatever diet they're trying to use to manage their mental health, or even managing their medications as they're going through all of that. The hardest part of my job is all of the behavioral change piece, the psychological piece, the habit change, the changing your mindset, changing the way you do things, and even the patterns in your day to increase the friction around some of the things that you've been doing every day for years and years and years. All of those pieces, those are the hardest pieces. The addiction work is really the hardest. It's also the most interesting, I mean, I think,
Right.
in a lot of
But
ways.
isn't that really what sets what we're talking about now aside? First of all, we haven't ever used the word calorie, or seldom used it in this discussion.
Yeah.
But isn't the challenge that the world, at least when it comes to this metabolic sector of disease, is trapped in the concept of changing what we're eating? And while that's a tiny component, the bigger issue, which I know as a specialist, you're focused on this, is why. Why are we overeating? Why are we selecting carbohydrates? Why are we doing this? There must be some enormous benefit to smoking, because otherwise people wouldn't be trapped in that. And if we don't address the why, changing the what is easy on an easy day, but on an emotionally challenging day, you're always going to default back to your why unless you've changed your why. And
Exactly. I mean, like what I like to say to people is, I've been saying this for years and years and years because, as a psychiatrist, I mean, it really doesn't matter. Any kind of healthcare professional is dealing with addiction, right? Because most of us have an addiction of some kind. And so what I, found myself saying to people over and over again is people aren't stupid. They do things for a reason, right? So when they come in and they say, I need help with drinking, or I need help, with cannabis, or I need help with opiates, or whatever it is that they need help with, or it's overeating. I never just say, okay, let's work on that. I say, well, tell me what it does for you. Like why, what do you like about it? How does it help you? What is it doing for you? And because that's not a question, I'm sure it's a question you ask all the time, but it's not a question they're used to hearing.
right.
They're used to people jumping to the, okay, let's work on this, but I need to understand what it means to you and how it's useful to you.
We have to
Of
replace
course
the
it is.
benefit with something that has
Yes,
full benefit without the liability.
exactly.
We, in addiction management, replace something good that
Yes,
causes harm with something good that doesn't cause harm. It's
exactly.
never a removal because that's deprivational. So
Yes.
another little, just I know we've gone a long, long time. So you would agree, even though it's not in DSM-5, and who's the woman in New York?
Well, then we can't discuss it.
Right, the neuropsychiatrist in New York, or neuropsychologist in New York, not Nina. She's done so much work with mice and rats. She's wonderful.
Oh, I know who you mean. Hold on, it'll come to me.
I need some fish oil.
Oh my gosh, her name begins with an A. It'll come to me.
Avina.
Oh, Nicole Avina.
Nicole Avina. My goodness. Okay, and I'm older than you.
Are you sure
Um,
about that?
I am definitely. You already mentioned your age, and I'm older than
I see. Okay.
but she's done some brilliant work on the addiction side, and her
Yeah.
challenge is that it's not DSM-5 recognized, so it doesn't exist. Like obesity was only a disease in 2015 when the AMA gave it a category. So, but you're very comfortable as a Harvard psychiatrist for working in this space. Now, and this question you may defer. Um, how do you reconcile at your wonderful institution the work being done at the Chan Public School of Health?
Well, full disclosure, I do not work at Harvard anymore. I haven't worked there
Okay.
for quite some time. But and the reason why, so I worked, so I trained, I did my residency there, and then I went away for a few years and worked on my own, and then I came back and worked for the Harvard University Health Service for 7 years, and then I left. And the reason I left, even though I loved student mental health, it was my specialty. So the reason I left, and I then went on 5 years of student mental health at Smith College, which is about 2 hours to the west of Harvard. So the reason I left Harvard University Health Service was because the directorship changed. And when the new director came on, who's no longer there, but when the new director came on, she was not comfortable with my incorporating nutrition principles into my work with students. She said, this is beyond the scope of psychiatric practice. So that is the main reason why I decided to leave. So I don't work there anymore. But
You've been doing this a very long time, the nutritional aspect, you've been
yeah,
doing it a long time.
yeah. I started studying it about 15 years ago, and more than 10 years ago started using it in clinical practice. Yeah.
And how do you feel about that conflict with a lot of the work being, that's a use of a four-letter word that is inappropriate. The publications from the Chan Public School of Health that
So
conflict
you could
everything you and I believe in.
you could replace the word work with guesswork.
I like that. Yes.
So, but so I actually took a course at the graduate at the Harvard School of Public Health, a graduate course in human nutrition when I first became interested in nutrition. Back a dozen more years ago. I and I was disappointed to find that most of what is taught there is based on guesswork. It is based on an unscientific methodology called nutrition epidemiology, where they just are using 50% of the scientific method, the hypothesis generating side, and they're not going on to step 2, which is the test your hypothesis. So they finished step one. They've got their theory about, you know, whether blueberries, you know, increase the risk of dementia, that sort of thing, and they publish it. They never test their theory.
Well, isn't a large part of their work to prove their hypothesis rather than to disprove it, which is the foundation of science? So they say, I've got this hypothesis, let me try to find a bunch of ways I can corroborate this, and if something doesn't agree with my hypothesis, we'll explain it away. I just threw that question out there, but I'm pleased, well, not pleased or displeased, but I'm interested that you're not longer there. One last question for you, because I know we've gone forever, and I really appreciate your time. Do you have imposter syndrome?
Yes. Why do you ask?
Because I do too. And the story goes this way, is that how can I be right when the entire consensual world out there tells me I'm wrong? And how is it possible for me to say statins are not a good idea? How is it possible for me to say it's okay to eat fat, it's not okay to eat an abundant? How is that plausible when everything says the opposite? And my imposter syndrome gives me a degree of humility in this space, but also is reinforced every day by my successful patients. But 23, 24 years into this field, I'm still petrified that I'm wrong.
Oh, I have a different form then.
What is your, yeah, so what is your, when you heard that, what did imposter syndrome, I shouldn't have led with my narrative. What is
Oh,
your,
no. I mean, that's actually, I'm glad you did, because at least my form of it is different. So I am really, I am not at all concerned that that the basic foundational principles of biochemistry, physiology, metabolism, nutrition, you know, the nutritional differences between plants and animals. I am not at all. I feel like I'm on very solid ground when I'm thinking about these things and writing about these things and speaking about these things. Um, but I also, I mean, my imposter syndrome really comes from, I think, just, you know, just being kind of constructed as a somewhat insecure person. I'm constantly questioning myself, and do I really have that right? Let me double check, let me triple check, let me ask somebody else, let me ask it a different way, let me, before I dare to say anything about this, I really obsess about making sure that I've done everything I can to to corroborate it before I share it. And there are lots of people who don't function that way in the world, and they also get ahead faster. You know, they accomplish things a lot faster. But you know, this book took me 10 years to research. Well, let's see, 15 years to research and 2 years to write, because of that perfectionism and that, like, oh, I'm not quite sure, and let me just check, and I would hate to mislead somebody. I would hate to say, you know, that sort of, that level of responsibility that really none of us can ever really achieve. I mean, of course, I'm going to make mistakes. You know, of course, there are going to be pieces that need to be corrected later, but I feel very solid about the foundational principles of the work that I've done. I think my imposter syndrome comes into play, meaning that, you know, what am I doing? What am I doing? When people say, when they describe me, you know, as, you know, one of the pioneers in the field or a thought leader, that's what I think. Me? That's that's
well,
my version
right.
of
So
imposter syndrome. Like, you're talking about me.
yeah,
Um,
that's but along those lines, have you ever regretted advocating a diet or a nutritional approach to someone that could have benefited from a medication that you didn't prescribe? That's a tough question, but I always have to be so cautious that I don't not, and I get bashed by our community, the ketogenic community, for sometimes prescribing medications or even doing surgery on somebody. But there are people, if I've got those tools, that have tried really hard. I don't do it as an alternative, but have tried really hard and struggle. They just struggle. I struggle.
oh my
And
gosh, of course, of course.
so there are places where we can use medications to stay
Yes.
or to help. I know your practice has changed in terms of prescription, it has to have, but are there times when you've regretted saying I was too deep in the nutritional hole and I didn't see the wood for the trees in terms of this person's where a medication could have benefited a person and you didn't necessarily prescribe it, or you
Well,
did.
I have to say that with every person, I give them the choice and then I make a recommendation, right? So I say, well, what are your what are your goals? Which road would you like to take? And I will support you on whichever road you want to choose if I think it's safe to do so, right? So I will weigh in about whether I think, this is not the right situation for a diet because this is a crisis, or this is a situation where I'm not really sure that diet is playing enough of a role for it to be worth it for us to try this right now. Let's come back to it later. So I used to do that all the time. For years I worked in traditional conventional settings, not just private practice, but also clinics and universities and group practices where I was using both methodologies depending on what the person coming in wanted. Ever since 2018, when I left Smith College and started using only sort of food first or nutrition and metabolic psychiatry, everybody who comes to me is coming to me for nutritional metabolic approaches.
They've already self-isolated themselves. They've already
They
inquisitive.
have self-chosen, right,
Right.
they've self-selected, but that doesn't mean I don't use medication still, right?
So
So
what
a
is
lot
your
of these
favorite
people are still
medication?
taking medications that need to be managed. And also some of these people the diet doesn't help them.
Absolutely.
And,
Or it helps, but they need help with it.
or you have to use a combination, right? And
Right.
so, I mean, I remember you asking this question at Swiss Re, what about GLP-1s? And I've recommended GLP-1s to a small number, but still certain patients who they were just struggling mightily
Well, they also have a
with the
profound
diet.
effect on the brain. I mean, that's where they're
Yes,
active. So yeah,
yes.
but they're a tool that we use along a journey, not an outsourced endpoint. And I think that's the big difference is when you write the script, off you go, eat less Oreo cookies, that's problematic. But if it's ancillary to your efforts to change behavior, in my opinion, then it's a tool that you use in a positive way. What is your favorite psychiatric drug? Last question.
Oh my gosh. I can only pick one.
Well, give me a couple.
So I'm a big fan of stimulants, and I'm a big fan of lamotrigine. Lamotrigine is one of the most useful.
What is the trade name for lamotrigine?
Lamictal?
Lamictal,
Yeah.
which is an antipsychotic drug.
No, it's an anticonvulsant.
Oh, sorry, an anticonvulsant,
That's
yes.
okay. Yeah, sure. Yeah, so, and the reason I like it is because a lot of people who have depression don't respond well to the serotonin medications and the SSRIs and the SNRIs, medicines like, Prozac and Celexa and, Zoloft and Effexor and Cymbalta. And a lot of people with depression actually have a degree of mood instability. If you really take a deep enough history, often there is more of a bipolar element to it, even if it's not frank bipolar disorder. And Lamictal is a much more reliable antidepressant for more patients I have found than the SSRIs.
Okay.
So yeah, I really think it can be very helpful.
And you don't find it slows people down too much?
It can. I mean, one of the problems with all of the anticonvulsants is that you can get some cognitive side effects. Lamictal is one of the least likely to do that. Topiramate is one of the worst. So, I had a third grade teacher who her students were correcting her spelling on the board because she was taking 50 milligrams of topiramate. So, but lamotrigine is less likely to do so. On the higher doses, you will see it. You will see people with word finding problems. You'll see people just not as articulate as they're accustomed to being. Every psychiatric medication has side effects. Every medication has side effects. But I do find Lamictal to be useful for people who are using who are looking for antidepressant medication. That is one of my favorite ones for the right people. It's not for everybody. And the stimulants I love because they are so effective so quickly and are easy to stop and start. I think the trick, of course, with stimulants is figuring out who is the right candidate for stimulants.
Is Lamictal useful in ADHD? Is it a drug that can be used in lieu of the Ritalins and that type of thing, or not so much?
I haven't ever used it that way, but I'm not saying that it couldn't be, but I certainly haven't ever used it
I'm
for
just because we
that
have
purpose in
such, I
mind.
have a nurse, a psychiatric nurse practitioner that I work with. I employ her for exactly because we see so much psychopathology, and she can
Yeah.
do both the therapy and the treatment. And I'm going to talk to her about this, but you know, we really struggle with folks that come to us on all these ADHD drugs. Either they can't get them anymore, or they're not working, or they're abusing them for weight loss. Same thing with Cymbalta. Cymbalta is a first-line drug. I find, and again, I'm not a psychiatrist, but it's so difficult to. I've had people open the capsule and take it out
Oh,
grain by grain to
yeah.
wean, and
Me
yet
too.
it's
Yeah.
prescribed like almost as much as statins.
It's true. Cymbalta and Effexor and Paxil as a close third are very difficult to taper. Really, really painfully. And the fact that they come in just these discrete quantities, that the dosages that make it almost impossible to taper is just, I mean, the pharmaceutical companies don't understand.
Oh,
You
they
know,
do. They do because it makes money.
oh well.
Again, and I'm very jaundiced in my thinking about that, but
Yeah, it could be. It could be. Yeah, it's just it makes it almost difficult. It makes it almost impossible to taper.
hmm. Well, this has been, I know it's been a long, long time. Certainly nerded out. When I sit back and I say, wow, I learned a lot. And
Well,
I,
me too. I mean, you've asked me questions I've never been asked before, which got me really, I even took some notes like, oh, I want to look this up. I want to look that up.
by the way, Dr. Ede has written a book.
Oh, right.
Yes. And it really is, there it is. Yeah, absolutely excellent. It is change your diet, change your mind. It is a narrative of what we've talked about. I try to go through some of the chapters and then we get lost off the beaten path, but it really is exceptional in this space. And I think it bears
Thank
the biggest problem with your book right now is your own humility and not publicizing it more, because this deserves to be at the top of book lists. It really does. And I don't blow smoke where it's not deserved. This is a big deal, and it really is a wonderful, wonderful book. So thank you very much for publishing it, and I hope you're already working on edition number 2.
Oh, my family would not be pleased with.
Yeah, no. This is really an exceptional book. It really is wonderful and very, very impressive work. And just thanks for being you.
Likewise, and thank you very much for your very kind words about the book. If it helps people improve their mental health, then it was worth it. And if it helps change the nature of the conversation about nutrition, which I would love, you know, for it to be less polarizing, be more constructive, that would also make me really happy.
Do you see patients with telehealth? How can people access you if they want you as a psychiatrist or guidance in terms of the metabolic psychiatry? How do people access you?
Yeah, so I do see patients in Massachusetts. I have a bit of a wait list, but I do see patients in Massachusetts where I'm licensed, and I also consult to practitioners outside of beyond state lines, and also the clinician directory. So if people are looking for a metabolic psychiatrist or a practitioner, really of any background, to support them transitioning to a ketogenic diet in the context of a mental health issue like depression or anxiety or ADHD or bipolar disorder, schizophrenia, and you're looking for a practitioner to guide you on a ketogenic diet, which is really important, not to embark on a ketogenic diet without learning more about it and consulting with a skilled, knowledgeable practitioner. Then I have a free clinician directory on my website. The website is diagnosisdiet.com, and there's a tab, Clinician Directory, that's free to search. It's international, it's growing every week. So please do that, because if you're interested in ketogenic diets for mental health, and this explains a lot about how to do it safely, the book alone is not enough. You do need to work with somebody, especially if you're taking any prescription medications, if you have a history of any serious psychiatric symptoms, or if you have any existing health problems, because the diet itself is not dangerous. The transition to the diet needs to be carefully managed to be safe.
Exactly. It's a transition. It's not start
Yes,
tomorrow and jump in the deep end of the pool. It doesn't work.
exactly. Yes, please.
The tortoise, not the rabbit.
Exactly.
Well, this has been
Thanks so
wonderful.
much, Rob. Yeah, it's great.
Thank
I
you.
really enjoyed it.
Take care.